Welcome to Electricity Week. In Electricity Week, we're not going to look at every single thing in electricity at the entire syllabus because it will be a 4-hour revision lesson. In this, I'm particularly concerned about potential dividers and also internal resistances. There are other parts of electricity like resistivity, power, or charge that is required in electricity, and in particular the VI characteristics of diode, and also a few required practical that you have to learn. But in this video, we are not going to go through it because it's too short. But I'm going to go through the most important part, the most difficult part. Okay. As usual, accompany PowerPoint on that. So question 1. Let me remind you, you can do these questions before I say so. If you have a question, if you do not have the question, do it and skip it to the question 2 and stuff like that. Yeah. Question 1. A gas containing doubly charged ions flows to give an electric current of 0.64 amps. How many ions pass through a point in 1 minute? So in this one, I just want to make sure you understand this equation. I equals Q over T. What is I? What is Q? What is T? I is current, Q is charge, T is time in seconds. Charge is in coulombs and current is in amperes. So let's begin by substituting these units, the numbers in the equation. And this is 0.6. For A, charge in here is what we're trying to find. This is total charge. And the time will be 1 minute. So 1 minute will 1 times 60. So total charge in here, put it in a calculator, is 38.4 coulomb. Okay, they're asking you for how many ions. So it's very, very important for us to know this is the total charge, right? That's total number of coulombs. How many charge is 1 ion? We know that 1 electron is 1.6 times 10 to the power minus 19 coulombs. This is in the formula booklet. You have a look at your formula booklet and you will know this. And it says that it's a doubly charged ion. That means it's a 2 plus or 2 minus. Alright, so doubly charged ion, doubly, that will be 3.2 times 10 to the 19. This is per ion. If this is per ion, and per ion is this coulomb, total coulomb is this, that means that how many ions will be 38.4 over 3.2 times 10 to the power minus 19. So this is going to give you 1.2 times 10 to the power 20 ions, which is C. Okay? Alright, so that's question 1. Try question 2. Okay, question 2. Question 2, it says that EMF is 12, and this is the circuit. What is the reading on a voltmeter connected between point X and point Y? When you have a voltmeter, you are getting the potential difference between these 2 points. So potential difference will be how many volts is in this point and how many volts in that point, and what's the difference of that voltage. This question I'll put it down to remind you a few things. What is the potential difference? What is voltmeter measuring? Voltmeter is measuring the difference in potential. How many volts in this one and how many difference is in these 2 points. You can't actually get a potential difference of just 1 point because there's no difference of that 1 point. Anyway, yeah, let's do this. So firstly, our two equations really quickly for potential dividers is V1 over V2 equals R1 over R2. That means that this is only in a series circuit. If it is a combination of series and parallel, you can't use this. You have to reduce it to this form. That's R1, R2, V1, V2, and then I know a V total in here in order for us to use a potential divider equation. Equations like this, R1 and R2, R3 is no good because in here we've got parallel circuits. So this needs to be combined in the series circuit before we can use this equation itself. Talking about these two, talking about this, we also really need to, if you are aiming for A, you will need to actually really quickly determine what the potential divider of these is. For example, if it is like this is not in the question yet, but there's another question that like that to come. If this is 2 ohms and 2 ohms, and I've got 12 volts, how do you split it? Because I know that V1 over V2 equals R1 over R2. These two resistance has the same resistance, so they should receive the same voltage. So if they share this 12 volts, that means that this is going to be 6 volts and this is going to be 6 volts. Alright, let's look at this one. If this is 2 to 1, that means that R1 and R2, R1 will be equal to 2R2, okay? And they all share 12 volts. So 12 volts, how many parts do we need? We need 3 parts. So 1 part is going to be here, 2 parts is going to be here. So actually, it is going to be 4 volts and 8 volts. If you don't like this, that's completely fine. If you can't comprehend this, it's completely fine. Use this. So V1 over V total equals R1 over R total. Let me do R1 first. R1 is 2, R total is 3. So V1 over V total, I'm trying to find V1. V total is 8. So V1 must be 2 over 3. Sorry, V total is 12 because each branch has 12 volts. So in here, V total, V1 is 8. So if V1 is 8, V2 will be 12 minus 8, so that's 4. The same thing happened to here the other time. So this is 3 and 1, 3 to 1. That means that this is 3 times as much voltage as this one. In total, there will be 4 parts. 4 parts. So 12 divided by 4 is 3. 3 volts, 9 volts. Is that right? Because 3 times 3 is 9. So this is right as well. So in this situation, if we are looking at this point and this point, let's say I'm going through in this direction. In here, from 12 volts, in here I'll have 8 volts in here. In here I'll have 9 volts in here. 8, 9, the difference in potential is 1 volt. Okay, it works in the other direction as well. But in here, 8, 9, the difference is 1 volt. That's why the reading of a voltmeter connected in X and Y is 1 volt. Okay, do question 3. Okay, question 3. A potential divider circuit consists of battery connected across a thermistor and a variable resistor in series. So whenever you do circuit questions, 100%, first thing you do, no matter multiple choice or anything like that, redraw a circuit. It doesn't take 2 seconds, and please, whatever you do not use a ruler. This will suffice. Yeah, quickly do the circuit like that, so you can actually draw what is it that you're talking about in the circuit. Otherwise, you will never be able to do any potential, any circuit questions. All right. So which one of the cases will cause potential difference across the thermistor to increase? Remember, we want thermistor. So I've labeled this RV for variable, VV for variable, RT for thermistor, VT for thermistor. So we want to see the variation of this, and we want to find which one VT increases. Okay, so this is VT increasing. So let's see the 4 options now. Increasing the temperature of the thermistor. When you increase the temperature of the thermistor, you actually increase the number of ions available. So in that situation, resistance will decrease because you have got more electrons, more ions. Your resistance will actually decrease for thermistor. For anything else, if you increase the temperature, resistance increase. But for thermistor, increases temperature, resistance decrease. So, yes. So in here, let's look at what they're talking about. Increasing the temperature of thermistor. If you increase the temperature of thermistor, our thermistor decrease. If our thermistor decrease, V thermistor decrease as well. But we want it to be increased, so the answer is not A. Alright, B. Increasing the resistance of variable resistor. Increasing resistance of variable resistor will increase our V instead. If you increase the variable resistance here, increase RV will increase the voltage that's received by variable resistor instead. So if you increase this one stays the same, EMF is not changing. So the voltage received by the thermistor is also going to be decreased. So this is what we want. This is not what we want, so that is not okay. So B is also not okay. Let me write this out. And C, reducing the EMF of the battery. Reducing EMF of the battery will decrease both of these. Also not this. So that is not okay as well. Okay, the last one is going to be adding a resistor across the variable resistor. So they are asking us to do this. When you add resistor in here, resistance in parallel, this will always decrease. As you add more resistors in here, 1 over R1 equals 1 over R total, 1 over R, 1 over R. Whenever you add 1, it will always decrease. So RV is going to decrease. If RV is going to decrease, VV is going to decrease as well, the voltage that is in this part. If there's less voltage in this part, there'll be more voltage in this part. So D is going to increase VT, which is what we want. So that's why the answer is D. Alright. Do the multiple choice 4, 5, 6, 7, and 8, and we'll come back and I'll give you hints to do question 9 together. It's not easy, but we'll do it together. Okay? Alright. Good, question 9. Question 9. The diagram is like this. They are saying that the supply has negligible internal resistance and resistance of 750. Thermistor has 750 ohms at room temperature, and the students want the potential difference to be 5 volts in here. Remember, what's the first step you do when you're doing a circuit question? We draw the circuit. So always draw the circuits first and put down as much information as possible. This is going to help you immensely. So you know that if you want this to be 5 volts, the first thing, what do? You know the top will be wants to be 9 minus 5. 9 minus 5 volts, which is 4 volts. The top here you want to be 4 volts. The bottom here you want to be 5 volts. So before anything, we could already deduce that already. So really quickly, we have some sort of different ways to do the same problem, so you're not going to be lost. So the first question is actually not anything to do with potential divider, but it's good revision anyway. So it says that the 0.5 k ohm. So first thing I did is put 0.25 k ohm into ohm first. I like to do this because you're going to trip up otherwise. I'll even, when we receive the paper, I'll actually cross out K ohms and actually do ohms as well. One last thing to worry about. It's made of 50 turns of the wire. Turning a wire, that means you have a cylinder, and then the wire goes around it 50 times. So is that actually giving us area, cross-section area? Not really. So this is actually 8 mm in diameter. So resistivity of wire is that determine the area of cross-section area that has been used for the resistor. So I want to remind you of this equation: R equals rho A over L. Rho is resistivity. A is, what is A? It's diameter of wire of the, it's a cross-sectional area of the wire. So you cut the wire in half, and usually the wire will be circular, and that is the cross-sectional area of the wire. This is the length of the wire, and this is resistance, and this is resistivity, which is a material property. For example, copper will have lower resistivity than steel. Silver, which is the best, one of the best metals of resistance, it will be lower than copper. So in here, when you turn 50 turns, this is not actually giving you the cross-section area, this is actually giving you length. We don't know cross-section area because they're asking you for cross-section area of the wire. So in here, I'll actually let you do this. Substitute into the equation, then you should be able to do question A. So if you want to pause the video into question A. Okay, question B. The student selected resistor rated at 0.36 watts for the 0.25 kilo ohm resistor in the diagram. Determine whether the resistor is suitable. In the marking scheme, there are 3 different routes of answers. The other route of answer is talking about all 9 volts going to here. When can all 9 volts go into here is when the resistance of this is 0. This is one. Can it be 0? Yes, it can be 0, because if you are heating it into maximum heat, maximum hotness, this is going to turn into 0 ohms. Because it's a thermistor. Thermistor, high temperature, lower ohms. So if this is 0 ohms, then all 9 volts will go to here. Why? Because V1 over V2 equals R1 over R2. If R is 0, if R2 is 0, V2 is 0 as well. So there's an answer that's in terms of maximum. I'll actually do this with you as well. So if this one I'll say R2 total equals 0, all voltage, all 9 volts will go to R1, which is this one. Yep. So if you do this, the power rating, power equals V squared over R. V squared is 9 squared over 250, and that is going to give us 9 squared over 250. This is going to give us 0.324 watts, and that is our power rating over there. Our power rating is 0.36 volts, so that is very, very, very similar to the power rating. But there's also another answer for this that is acceptable as well. If you want this to be 5 volts and this is going to be 4 volts, let's look at the answer well, like a power of this when it's operating power. So 4 volts in here, 4 squared over R, 250. So this is going to give us 0.064 watts. You can say that it's lower than the power rating. So that is okay as well. Okay, so the next part is determine the R value the student should submit. I'm going to rock the board and come back to it straight away. Alright, the next part C is 5 marks. Okay, 5 marks. Hi, question 9. This is going to be question 9, question 9C. Question 9C. So we know that V1 over V2 equals R1 over R2 total. This is V1, this is V2. So I'm going to redraw the circuit so it's much more simpler. So this is the combined of these two R. I call this R2 total. This is R, and this is 750. So we actually know that R2 total, 1 over R2 total equals 1 over R plus 1 over 750. Okay? That's a combination of these two. Alright, so we also know that in the other one, we want this to be 5. So 9 minus 5 equals 4. So we can substitute it in this equation. 4 over 5 equals 250, which is top R over R2T. So using our calculators, we can actually deduce that R is, R in here is 375 ohms. Okay, R2 total is 375 ohms. Substituting back to that equation, 1 over 375 ohms, it will be equal to 1 over R plus 1 over 750. Okay, so 1 over R will be equal to 1 over 375 minus 1 over 750. So R in here will be equal to 535.7, which is 540 ohms, because the entire question is giving us 2 sig-Figs. You need to stick with 2 sig-Figs. Okay? Alright, 9, question D. State and explain on the effect of output increasing temperature on the thermostat. Increased temperature on thermostat is going to reduce the resistance. If you reduce the resistance in here, you reduce the R2T in total. If you reduce the R2T in total, you reduce V2 in total. That's why the output of thermostat will decrease. Okay? Alright, I want you to try question 10 and question 10 by yourself. And we will come back to question 11. I'll give you some hints for question 11 as well. Okay? Welcome back. Just some hints on question 11, and I'll let you do it by yourself. So, question 11, they're giving us a power rating. Power rating doesn't mean anything. Power rating actually only gives you one thing. What's that one thing? Resistance. Because sometimes we don't have the operating voltage. If we don't have the operating voltage, we wouldn't have the operating power. So, before we do anything, let's find out the resistance of A and C and B and D first. So, if resistance A and C will be V squared, or rearrange this equation, R will be V squared over power. So for A and C, it will be 6 squared over 6. So resistance will be 6 squared over 6, which is 6 ohms. B and D, resistance will be V squared 3.5 squared over power, 4.1. So that is going to be 3.5 squared divided by 4.1. So that's going to give us 2.98 blah blah blah. I'll say it's 3 ohms. First instant, write this down. 6 ohms, 6 ohms, and then we got 3 ohms and 3 ohms. So if this is 9 volts in here, and this branch is 9 volts, this branch is 9 volts. What's the ratio? This is 1 to 2. That means that this, so, or you can use V1 over V total equals R1 over R total. So R total is 9, R1 is 6, V total is 9, V1 must be 6 as well. So this will actually get 6 volts, this is going to get 3 volts, 6 volts, 3 volts. What's the operating voltage? So A and C is actually okay because this will meet its operating voltage. B and D, the operating voltage is 3.5, it only gets 3, so it's dimmer. So these are going to be dimmer, this is going to be brighter. So B is completely the same. How many volts is in here? How many volts is in here? So what is the potential difference between these 2 points if something is put across that? So that will be your answer. Okay, try question 2. Try question 11, and then we'll do question 12 together. So question 12. In the circuit shown these voltmeter high resistance internal blah 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 blah. Which of the following is not equal to the EMF of the cell? So firstly, A. It says that the reading of voltmeter when switch S is open. When switch S is open, that means that the load resistance in here will be there's no load resistance at all. It's all open. It's not connected. So in here, this EMF will be equal to this instead. So yes, EMF will be equal to load resistance in here. B. The chemical energy change to electrical energy when the unit charge passes through the cell. This is the definition of EMF. If they ask you what is electromotive force, that is the chemical energy change to electrical energy when the unit charge passes through the cell. So write in your notes right now. C. Twice the reading of voltmeter when switch S is closed. You need to see that in this particular question, R equals R. So what is that actually saying? That is that EMF equals IR plus IR, which is V in plus V out. That means V out equals V in. That means that this is V out, that's going to be V in. So EMF is equal to 2V in. So yes, this is actually yeah. Okay, so the last one. The electrical energy produced when the unit current passes through the cell. This is incorrect because the energy produced, this did not account to the energy wasted in the internal resistance. But for energy as thermal energy. So this is not equal to EMF of the cell. Okay. Question 13 is very, very typical internal resistance equation question. Please try it yourself using this. Remember, V out equals IR, V in equals IR. Okay? Please try it yourself. And if you, I will go for it, but try it yourself first. Okay. Let's do it together now. So it says when it's open, EMF is, when it is open, that means that it's equal to EMF. So EMF is actually equal to 1.45. When it's closed, it's actually measuring the voltage V out outside. So V out is going to give us 1.26. So because we know that EMF is 1.45, V in plus V out is 1.26. We know that V in, the voltage that's the potential difference in the internal resistance is going to be 0.19. Okay? But also, we know that our load resistance in here is 10 ohms. So V out equals I times R. We know the load resistance is 10 ohms. We know that the V out is 1.25. So we know that the total current in here, because it's series circuit, total current is same everywhere, will be 0.125 amps. We know what this is the current. We know V in. So we can put it back to this equation. V in equals IR. R being the internal resistance, 0.125, and V in is 0.19. So R in here is going to be 1.5 ohms. So the answer is D. R being internal resistance. So you need to have a good grasp of what is going on and what's big R, what's small r, and always write these down. So in here there are actually four equations. Equation number 1, equation number 2, equation number 3, and equation number 4. Okay, you need to use this in order for you to understand the thing. Try question 14. Question 14. If you don't understand question 14, you need to read the marking scheme, because after reading the marking scheme, you will understand question 14 instead. Remember, there's internal resistance. Internal resistance will add to the total resistance. Okay? Alright. Alright, the last question is question 16. Question 16, I want you to try A. If you don't understand this, please go through the marking scheme, have a look. Very, that's quite practical that we usually do that. Alright, so B is these two diagrams. So these two diagrams, we have got left hand side, we have got resistor, which is 6 ohms, and on the right hand side we have got a cell with internal resistance. So we're going to put the numbers down as well. Each one of these are 0.7, 0.7, 0.7, 0.7, 0.7, and the internal resistance is 8 ohms. A lot of internal resistance, but that's what typically happens when you have a solar cell, like a solar panel. They have got loads of resistance. That's why they are still very inefficient in these times. Anyway, so let's see. Our goal is to get a current of 75 mA. So let's try to see what the current is. This is the goal. So this is what we are not going to use in our calculation, but that's a goal. So for this one, very easy. V equals IR. What's V? V is 0.7 volts. Oh, let me put down the volt in here as well. 0.7 volts. I is going to be what we don't know. These two are series, so 6 plus 8. So I is going to be 0.05, which is 50 milliamps. So this is not going to be okay, because our goal is 75 milliamps. The second one. Let's look at the total V here. These two are in parallel, so this is going to give us 0.7, because each branch is going to give 0.7. It's still 0.7. It's not added together, and this is going to be 0.7 as well. So total V is going to be 1.4, because it's 0.7 plus 0.7. So in here, it's going to go 0.7. In here, it's going to be 0.7 volts. So we know that in total V equals IR, V total is V total is going to be 1.4. I total, which we're trying to find. So what is R total? R total in here, combine these two together, 1 over R equals 1 over 8 plus 1 over 8, and that R will be 4. So it will certainly, so these two will look like this, 4 ohms, this is 8 ohms, and also that's the 6 ohms in here. So our total will be 6 plus 4 plus 8. So in this situation, I total will be 0.07777, so that will be 77.77 milliamps, and this is bigger than 75 milliamps, so we can use this instead. Okay? Alright, this will conclude our electricity revision. Obviously, there are more internal resistance questions that you can do, and please do them as well. I'll give you some more help when I next see you as well. Okay? Thank you.